In this video, we're going to start to take a look at the arc length of polar curves. I'm actually going to leave example number 4 here from the notes as another one for you to go ahead and try on your own. Now, if I take a look at the arc length for a polar curve, the way that I could start to do this is, again, to import ideas that we had in the previous section about parametric curves and their arc lengths. So again, we could start to see that if I want to consider the arc length of a polar curve, I can imagine that if I have an equation of r is equal to f of theta, where my values of theta maybe range from a to b, and I want the arc length of this, then we can view this curve in terms of parametric equations, which again could be x is equal to r, which is f of theta, times the cosine of theta, and y, which is f of theta times the sine of theta. Now again, it doesn't really matter whether I use r or f of theta, as they are indeed equivalent. So you can leave this kind of in whatever form you prefer. In fact, if we were in class doing this, we'd have a lot more board space to work with, and I would typically be working in the following steps with a r cosine theta and an r sine theta to demonstrate some things. So here's where we can actually start, though. Once I have these parametric equations, to find my arc length, I can say that we know from 7.2 that the length for a parametric curve is given by an integral from a to b for my parameter. Notice then that this would have to be a d theta integral because I'm dealing with parameter of theta. And then I would have my dx d theta squared plus my dy d theta squared. So I can go ahead and actually do this every single time to go ahead and find the arc length of a polar curve. Again, as long as I know how to do this green parameterization, everything is good. But we're going to go ahead and actually try to take this one step further. So I'll say here that we can show, it's actually possible to demonstrate that if I was to take dx d theta and square it, and my dy d theta and square that and add them together, that is, I'm looking at what's going to be underneath this radical, I could see that I'm going to end up with the following. I'm going to end up with, well, let's see, the derivative of my x would be something like my dr d theta, notice this is where I'm using this r notation, times the cosine of theta, and then I would be able to reverse this with an r and a sine of theta. But of course it's going to be a negative sign, and so I'd have to change this plus here to a subtraction. So this being squared, and then my dy d theta is going to be my dr d theta times the sine of theta plus r times the cosine of theta. And that's all squared. And oops, there shouldn't be an equal sign in between these, but this should be a plus. So again, what I'm doing here is I'm just substituting in what my dx d theta and my dy d theta are, so I can understand what's going to appear here underneath this radical. Well, with a lot of additional simplification that we can't unfortunately go into a bunch of detail here, we just don't have the space for it, but you could easily go ahead and confirm that if you were to actually square both of these quantities and multiply out everything that's there, you could simplify this down to actually just be equivalent to r squared plus dr d theta squared. What this means is that it's actually possible to represent the length of our polar curve with this parametric representation, but also with this representation that again only uses r's and thetas. And so we can go ahead and state this as our formula for arc length. If we have the length of a curve with a polar equation, r is equal to f of theta, the range on theta goes from a to b, then that arc length is given by an integral from a to b, and I'm going to have my r squared plus dr d theta squared d theta. Notice the beauty of this representation, as opposed to sticking with what we knew from parametric, is that I actually don't now need to find that green parameterization, because I already know what r is, and it's really easy to take the derivative of r with respect to the variable of theta and immediately calculate what this is going to turn into. So this is the way that I would actually work through finding arc length. Now we can see a specific example here if we take a look at example number 5. We'll try to do this one here in the video, and I'll leave example number 6 as one for you to try. But let's take a look. I want to find the exact length of one tracing of the cardioid that's given by 1 plus sine theta. Now this was the same curve that we were looking at back in the previous videos. Here was the picture of the curve, and we want to go ahead and determine the arc length of this. So the first thing we would need to know is how long does it take to actually trace this full curve? Well, we had already kind of seen that 2 pi is how long I would need to trace this, but if I was a little unsure of that, I could always go ahead here and start to see that if I adjust the theta max value and attempt to regraph this, that I really need 2 pi in order to create the full picture. Notice that if I do something like 1.5 pi, I still don't get the full picture. I'm still going to stop short. And if I was to do something like much larger than 2 pi, like maybe let's say I do 8 pi, I'll see that I'll sketch the full picture and my wheel up here is still spinning. You can see it's kind of like regraphing the same curve over and over and over again. So I only need that 2 pi. So if I flip back to the notes here, what I'll see is that I can start by stating that we see that r equals 1 plus sine theta is sketched over the interval 0 to 2 pi. Right? So that's all I need. I just need theta to be in that particular range. So that gives me the bounds. But now I can go ahead and just say, well, based on what we saw up above, if I know what r is and I can square that, then I just need to be able to take dr d theta and square that. So let's see. If I go ahead and say my dr d theta is going to be equal to the derivative of this, that should just be cosine of theta. So I'll say also dr d theta is equal to this, and so my arc length should be an integral that goes from 0 to 2 pi, and then I should have my r that's getting squared, so my 1 plus sine theta, and then I can go ahead and square my dr d theta, which is my cosine squared, and I have all of this d theta. Now, of course, it's actually not too terribly difficult to work with this, because if I wanted to evaluate this integral, I can simplify a lot of stuff underneath the radical. Notice I'm going to end up with 1 plus a 2 sine theta, and then I'm actually going to get a sine squared plus a cosine squared, which I can just simplify down to a 1. So overall, I just have the integral of 2 plus 2 sine theta. And with a little bit of work, you could actually go through and find that this actually evaluates out to be 8. Okay? So that would be the length of that particular curve that we had in the picture. That is, if I take a look here, if I was to imagine maybe cutting this blue curve and unwrapping this, stretching it out perfectly horizontal and measuring it, it would be 8 units long. Now, if I flip back to the notes, I can see that how would the problem change if I was instead working with the function r is equal to sine theta? So like, what if I just got rid of that plus 1? Well, I can go ahead here, and if I go back, I can get rid of my plus 1 here and see how the picture would change. Okay, so I create this, and I can see that, again, I'm not really adding anything by continuing to sketch for this long of a time, as a yellow wheel up here is spinning. So I might need to go ahead and adjust what I have here. Let's go back down to 2 pi and see if we need this full thing. Well, notice it looks like I maybe graphed that multiple times. I can then maybe go ahead and continue to adjust this. looks like if I swap to maybe the value of pi, this graph's just one single loop, and then I'm done. So this here is actually going to be a circle. This looks just like a circle. It's a circle that has a radius of, well, let's see, maybe like a radius of a half, something like that. So if I was to go ahead and start to compute this, I could see that this function is traced once for values of theta that apparently go from 0 to pi. And so this is going to then change the bounds that I'm going to end up with on this integral. So my length here would be given by 0 to pi, and I would have my r squared plus my dr d theta, which again here is just going to be the cosine of theta, but squared. Now, of course, this simplifies down very, very nicely. This is just the square root of 1. So this is just this integral. Antiderivative of theta, or of 1 is theta, and if I evaluate theta from 0 to pi, I get pi. And this should actually line up perfectly with our intuitions about this question. Because if this was a circle with a radius of 1/2, which it looks like it is, then I would know that the length around the outside would be the circumference of that circle. And the circumference of that circle is given by the formula 2 pi r. And if that radius is actually just a half, then the length around the outside of that circle should be pi. So the important thing to note here with both these problems is that it's really, really crucial to make sure that we understand how long or how long the interval of theta values needs to be in order to create one tracing of our picture. And that might change even as I make subtle changes to my function. Like here I just got rid of the 1, and it meant that my theta range changed from 0 to pi, or changed from 0 to 2 pi to the range of 0 to pi. So this is something that's, again, very, very important to keep your eyes open for. Now in example 6, which is one I'll let you try, and you can try to go ahead and go to your calculator, sketch out what this picture is going to look like. You're already told a range on theta. But in some things where I might have a curve that kind of isn't specified with a range, I need to make sure that I think about it carefully and use my calculator to help determine what those bounds should be. So example number 6 is left for you to try, and of course, if you have any questions, please let me know.